Today we're going to talk about refraction. Dealt with refraction a lot. Dealt with glass, invention of glass. Glass was originally first seen, honestly, when lightning would hit sand and it would melt. It would form a glass-like substance. You could kind of see through. It was kind of dirty, of course. It's been supposed that glass was formed, somewhat early on in melting of sand and stuff. But now lenses, and what we're going to be doing with these lenses, the refraction that lenses do, they weren't really formed. They were formed a little earlier in the 1600s. It's been thought that Galileo was the first to really use them to make a telescope. But people have been dealing with refraction since time for man began. Why is that? Well, if you're hunting fish and you're going, or frogs, and you're going frog gigging. Hopefully, Thornburg, you ever go frog gigging? You probably. Ronnie's probably been frog gigging. Maggie, Blue Alice, you ever been frog gigging? No? Do you know what it is? No, you don't. Angel, I thought you'd know what frog gigging is. But frog gigging is where you take like a little trident like that. You kill frogs. Now, and you get them, and of course you eat them for supper. Now with frog gigging, lots of times a frog will be underwater, and it doesn't see you. Some of you above water, some below water. And when you're at an angle, or you go flounder gigging, some of you maybe would do flounder like this sometimes at the beach. I don't know if they let you do much of it anymore, but you used to be able to go flounder gigging. And you take it, use that, and you try to get the flounder. Now, if you're at an angle to it, you may or may not get it. Now, if you can be straight down, look on it, what you see is normally what you get. You'll pop it there. But if you're at an angle to it, and you're looking at that flounder, and you try to aim right at that angle, where you see that image of that flounder at, where you think the flounder is, you're going to miss it most every time. Of course, it depends on the size of the flounder and stuff like that. Why? Because light coming from that flounder, remember we said the object acts as an emitter of light. It doesn't really, it's reflecting it from other sources. But that light coming from that flounder is bent at the water-air interface. That light is bent. And it's actually bent, what we'll find out is toward away from the normal, towards the surface. Remember, normal is perpendicular to that surface. And so when we see it, we actually see that fish when we're standing on the bank looking at it, and we're thinking, if I could spear that thing, where would I throw it? Shoot it with a bow and arrow. Where would I hit it at? You're going to aim past it. It's actually in front of you. It's actually in front of you. And what's really cool, if you're on the other side, you're the fish. When you see that, guys, it's light goes in and out, and your eyes keep that light going straight. They actually see us. They think we're closer to them than we actually are. So, when you walk up to a bank and fish are looking up, they scurry forth real fast before you can get close. Why? Because for them the light is doing this, bending towards you. So they think the light's going straight out the way our eyes work, and they see us closer than we are to them. Real interesting like that. Let's try to explain this refraction and what's going on. We're going to use ray models for this. You can use wave model, but the ray model tends to work easiest for it. Let's just go ahead with this. All right, so refraction. So what is refraction? 34.3. Refraction is the bending of light. Bending of light. So when light bends, and normally in those cases, when it bends, going from one medium to another. You're going from one medium to another. Medium being what you're traveling in. The old, you wonder where that term comes from. You may have known the term medium from, the seances. You have the medium that would try to, conjure the spirits of the dead and everything. It was a lot of parlor games and stuff and tricks from this from the 1800s, early 1900s. Why do they call it medium? Because that's what the spirits of those that were dead would travel through to get to and to talk to their family and stuff like that. So a medium is what something travels through. It's the medium. Sometimes you heard, I think auger sometimes is a medium. That's something that bacteria may grow or something in some type of medium. That's what something's in. For our case, it's going to be what the light is inside or going from, what it's traveling through as it moves in this case. Okay? And what we saw was, and the Greeks saw this, that if you have light, and let's make this water, and this is air, and relative to the normal, got to be to the normal. The mathematics works. You can do it the other way, but the mathematics doesn't work out very well. Relative to the normal, if light comes in at an angle, it will be bent from air to water as such, so that the angle of incidence, we're going to call that theta I, angle of incidence. This is going to be theta R for angle of refraction. Let me write this out. Theta I, angle of incidence. Theta R is angle of refraction. And that's the way it works. We saw that. People have been noticing this for years, for thousands of years they've seen it. Now, the Greeks did the world work. They tried to predict it. They tried to come up with the mathematics from it. Honestly, it didn't work because trig had not been invented. And trig is what we use to predict this. The ratios of the unit circle. Once trig was invented, in the later, I think, 700s, 800s, 900s, what they said was, we're going to call this medium air, which really it's going to be a vacuum. We're going to say a vacuum to make it a little bit more precise. And we're going to call this, we're going to say n equals 1. And what is this n? N is known as the index of refraction. Basically, we're going to make ratios, okay? We're just doing ratios. And what we can say is, and if that's 1, water is going to have an N of about 1.33 for water. I'll show you where I get that here in a minute. And if we use ratios for these angles and for these indices, and I'll show you where this comes from, you can show that N1 sine theta 1 equals N2 sine theta 2. We'll call this 1 in this case, and this 2. One's incidence, one's refraction. It doesn't really matter. There's some kind of principal reversibility I'm going to get to pretty quickly. The book, I think they talk about it in this section. But I'm going to talk about it here in a minute. Now, you say, well, that's not a ratio, that's an equation. Well, let's set it up as a ratio. What I can say is that in sine theta 1 over sine theta 2, equals N2 over N1. All right. So the ratio of the angles, of the sines of the angles, gotta get the sines up, is equal to the inverse ratio of the indices. So if you got 1 and 2 here, you have to have 2 over 1 there. Okay. This is known as Snell's law. 2 L's there. Snell's law. Now, if you know German, of course, you'd have to do this equation really fast because you would Snell. Of course, that means run. Do it very fast. All right. That's your lack of humor for today, everyone. Jeremy is suitably impressed at my knowledge of another language. So, Snell's law. It describes incidence and refraction. Now, does it work backwards? And the answer is yes. There's something known as the principle of reversibility. Principle of reversibility. Hopefully that's in the frame there for the camera. This principle of reversibility basically says light rays can go forwards or backwards in the same direction. So basically what I'm saying here is I've got the light traveling from air to water. Say if I do it the other way around. Say I take light going from water to air. Question is, does it travel the same path? And according to the principle of reversibility, which is what we've noticed, of course, yes it does. So when I think of N2 sine theta 1, M1 sine theta 1, N2 sine theta 2, Snell's law. Does it matter which one is 1 or 2? No. Now what matters is if I'm consistent. If this is N1, this needs to be 1. If this is N2, that would be 2. Okay? If I'm going this way, I just need to call that 1 and this 2. That would be 2 and that would be 1. I've got to just keep it right the direction I'm going. So if I always make the light is in 1 and what is refracted to as 2, the second one, this ratio always works. Now sometimes you'll see this written as incidence and refraction. You see that some now. Traditionally, you see it as M1. You just see angle 1 and angle 2. But you can go through multiple materials sometimes, multiple layers of this, and you just treat it one layer at a time when you do that. Thin film stuff. Anti-glare coatings actually are a function of that. We'll get into that, I think, next chapter. So, Snell's law basically is there. Now, what are some values of index of refraction? Well, for a vacuum, N is equal to 1. If it's 1, it doesn't bend light at all. Like we said, water, N equals 1.33 about. If you look at glass, now glass can vary depending on what its material in it. So for glass, N equals about 1.5. You can make glass go up more than that. Cubic zirconia. So Melissa, if your lucky fiance buys you a cubic zirconium ring, to know the difference? Well, yeah, you take it to a gemologist, that's right. But one of the ways you can tell was measure its index of refraction. You can do that since you've had this class now. Because cubic zirconium has an N equal to 2.18. While a diamond, and we all know, guys, remember this, don't go cheap. Diamonds are a girl's best friend, not you. So, diamonds have an N of 2.41. They bend light even more. And for most naturally occurring objects, that's about as we can see through, that's about more than about anything. Diamonds are. And that's the reason a diamond sparkles like it does. And we'll get into chromatic aberrations later on and explain this. But diamonds, you know, cubic zirconium just isn't going to spread light out as much. It's not going to bend light as much as a diamond will. So if you really want to bend that light quickly towards that normal, go from air to a diamond. It will bend light very much. In other words, I should say quickly. It'll bend it a lot more than just regular old water or glass. Now, could you make diamond lenses? The answer would be yes. Would they be expensive? Heck yeah. Can we make diamonds? Yeah, we can make them. They cleave diamonds or cut certain, the crystals and stuff. But you can make diamond lenses. We'll learn about lenses. Lenses are fat when they got to bend light more. You wouldn't have to make the lens very fat. It could be relatively just a little bit of curvature on it. If you want to make a lens out of it. But that's index refraction. That is Snell's law. The book does an example of deflecting a laser beam. That's actually a pretty good example in your book, deflecting a laser beam. One thing I want you to notice, and I just did one side here. Let's look over here. So say we take a slab of glass, and we're going to send light from here all the way through this slab of glass. This is glass, air to air. Okay? And what I want to know, how does it come out over here? So let's bring the light to this point. And it's going to be some, I'll call this incident angle. For I there is called incident angle. What's going to get refracted? It's going to be bent towards normal, going from air to glass. Remember, the normal is here. The normal is always perpendicular. So it's going to hit here. Now the question is, once it hits here, what angle does it come out at? The refracted angle? Some angle we got to calculate? Or is there an angle we even know that would come out at right now? Frida, tell me. You don't like the object stuff. Okay. Irving. Very good. Very good, Irving. That's a very good answer. It actually will come out at that incident angle. Very good, Irving. It's good work. So this angle here would be your refracted angle. This angle now is your incident angle. So when light comes out, it's going to come out. I didn't draw that very good. Let me draw that better. It's going to come out. So these, if you could extend this out, those would be parallel to each other. It shifted the light over, but it comes out at the same angle. Interesting. And that's what example 34.3 lets you calculate. And they go through that. And that's a good little example to do. Something like that put on a test for optics. Now, I'll demonstrate for you that here in a little bit. There's also something known as total internal reflection. And I didn't have something. I didn't have this stuff. I couldn't find it. Professor Caldwell probably knows where it is, and I couldn't find it. To demonstrate it. But I can demonstrate it a little bit on a piece of glass here in a minute. I'll show you. Now, if you notice, you have signs and stuff. So if Snell's law N1 sine theta 1 equals N2 sine theta 2, what about a situation where, like over there, this is glass, air, and air. Is it possible for us to shine this in at an angle where the refracted angle, because as I move this way here, that's going to get bent more further away from it, from the normal, because it's going from high index to low index. So if I do this, it's going to get bent like that. This would be my theta refracted, or the second one, of course. Can I keep increasing this till that angle's 90 degrees? Can theta refracted equal 90 degrees? Mathematically, it should. Well, let's look at it for glass and see. So if I put this in, N equals 1 for air, N equals 1.50 for glass. My theta 2 is going to be 90 degrees. I want to know what my theta 1 is. Okay? So let's just set it up. N1. So it'll be, so 1 times, excuse me, we're starting here. So that's going to be 1.5 times the sine of, I don't know, theta 1 to 1 times the sine of 90 degrees. Well, what's the sine of 90 degrees? Well, it's 1. So, sine of theta 1, 1.50. Sine of theta 1 equals 1 over 1.50. These, by the way, there's no units for index refraction. Since it's a ratio, angle over angle, there's nothing there. So ratio over ratio, it just doesn't have a unit. So theta 1 will equal the inverse sine of 1 over 1.50. 1 over 1.50. And for glass, if you do the math, theta 1 equals about 42 degrees. So less than 45 degrees, less than halfway. What happens? This doesn't go out like that. It goes out like that. Light never leaves the glass. It would just go out straight. But what if I make this angle bigger than 42 degrees? If theta 1 is greater than 42 degrees, what's going to be my refracted angle? How much does it get bent? Well, it would actually start getting bent down this way. So what I can say, if theta is greater than 42 degrees, light never leaves the glass. Light never leaves the glass. And if light never leaves that glass, it is, we will say, totally, for all you valley girls out there, right? Angel, you a valley girl? No. Cameron, you a valley girl? No. No, go over there. All right. totally internally reflected. It's not just refracted now, it's reflected down. Dang. That's pretty cool. This is sometimes known as TIR, for total internal reflection. And this TIR actually is very helpful. And something we use a lot for the internet. And what is that? How is total internal reflections very helpful? Something we use for the internet. Anybody? Anybody want to guess? Anybody want to chat on their screen? Send me little hearts. No? I can't give live feedback. This ain't live feedback. Nobody? Please? Okay. Fine then. I'll tell you. Be that way about it. It's called fiber. All right, this last part kind of got chopped off. So what I want to talk about is a little bit fiber optics. So hopefully this should have been appended to the previous video. So I'm going to do a little bit here. And I'm going to show you a little bit of what goes on when light is refracted through glass. So I said, what is this total internal reflection? What is this? What's an application of it? It's fiber optics. And they transmit so much bandwidth. They're so useful nowadays for transmitting information. And basically it works the same way. So what happens is you've got light coming in here. It goes in at an angle of around 80 some degrees with respect to the normal there. So it's a really big angle. Really big angle there. All right. So, and this is one type of glass. It's called the core. And the outside of it, you got glass called the cladding. This cladding's got a slightly different index of refraction, such that if it comes in at, 80 some degrees with respect to the normal, it'll be like over here. You'll get total internal reflection because of that angle. If angle is greater than, and that's actually known as the critical angle. I should have said that earlier. It's often known as the critical angle. So light comes in. It just hits the other side. So, dang it, I can't get out here either. Hits the other side, and it just keeps on traveling through. And a lot of your information traveling from the United States to Europe, across the Pacific, there's huge optical fiber cable, it's basically bundled together, many optical fibers. And there's these cables going across the ocean. And actually, since it's just light, you could tap into it a little bit, and actually Russia has tried to actually tap into those optical fiber cables with submarines and robotics submarines. There's some issues there if you look that up. Now, what I want to show you, that's optical fiber. We have a lot of companies in town in this area that work with optical fiber. There's lots of good jobs in it if you like optics. So what I want to show you, let me get the light over here. And what I'm going to try to show is the scenario I just showed you. Okay, you can see I got the light coming partially through, and that's the one on top. But now all of it's going through. And you notice that's where it would exit if it wasn't refracted. You see that far side over there? But since it's refracted, you see it getting bent. It's not coming out at the same spot. And those 2 points are slightly shifted from each other. Now, I will say this. If you notice, you see a little bit of light reflected the first time it goes through. And then you actually see some, it looks like, hitting that far side, bouncing back, and then going back out. when light is refracted and it hits an interface, certain amounts are always reflected. I'm not going to get into that right here, but that's the effect you see with the light coming out the back side. I really only want to look at what we showed in class, how there you can see the exit point for refracted light there, and when I shine it over, that would be the exit point for if it wasn't refracted at all. That's pretty cool. Okay. Let me see if I can show you total internal reflection here. You can see here we have some partial reflection. When I make the angle so big, when the light hits that side over there, that prism, none of it, as you can see, really comes out. None of it comes out. It all gets reflected off that side and comes out over here. If I make the angle closer to it, you can see a lot of the light gets refracted. But now at that angle, shoot, it all is coming. And right there, you can definitely see angle so great. No, it's reflecting at that interface, not being refracted. That's where you get some being refracted right there. There's a little bit being reflected. I think we address that a little bit later on. That can be a polarization issue and stuff like that. All right. Hopefully that helps.